Okay, now we're talking about elastic and inelastic collisions. Elastic collisions are bouncy collisions. Inelastic collisions are sticky collisions, and that's kind of the easy way to remember it. Things that are going to hit together and stick together are inelastic collisions. Things that are going to bounce off each other are elastic collisions. Now, elastic and inelastic are kind of extremes. There are no perfectly elastic collisions. There are no perfectly inelastic collisions in the real world. Now, there are some that are fairly elastic, especially at the atomic level. In chemistry, you're going to talk about ideal gases, and we're going to talk about the collision between the molecules of an ideal gas to be a perfectly elastic collision. And it's relatively close, actually, so that's something that you may encounter one place you do see it. So let's take a look at this real quick. A lot of y'all have seen this before. Oh, that's a thing of beauty. Momentum is conserved. These are fairly elastic. Watch this when I pull 2 back. The reason it has to do that is because not only is momentum conserved, kinetic energy is also conserved. And if I pull all 3 of them back, you got a pendulum. That's so cute. Okay, so let's look at the numbers behind this. So we're talking elastic and inelastic collisions. The key thing again, bouncy, sticky. It's kind of the easiest way to remember it. Now, we know that P is conserved, and P is always conserved. It's not just a good idea, it's actually the law. Momentum has to be conserved. The difference is, in a perfectly elastic, kinetic energy is also conserved. In a perfectly inelastic collision, Ke is lost. So again, in reality, there is some... It's almost like a sliding scale where you have elastic on one end and inelastic on the other end. And this is perfect. This is perfect. But most of the things happen in here. Now, things that are more towards the end, tackling in soccer and in football, usually is more towards the inelastic side. Things like billiards and pool would be more towards the elastic side. So that will kind of help you. Now let's take a look at the bouncy balls for just a second. And let's take a look at this happening. Now, when I have one ball going in to 2 balls and they're all equal mass, that's my before case. My after case is this. One ball coming out, and we've seen that. Now, momentum we know has to be conserved. So if we have this has a certain V and a certain M, this M is going to have the same V. So that kind of makes sense. Now, momentum, though, could be conserved if 2 balls came out. Could. Now, it's not what happens, but it could happen after if this happens. If you had 1 ball out and these were each V over 2, because those are each M's, momentum would still be conserved in that case, but Ke would not be conserved. Ke initial is not equal to Ke final. So that's not what actually happens. Because of kinetic energy, it has to be conserved. Now, here's the key thing. If you have a problem involved in that, what's going to happen is you get another equation. Not only can you create a momentum table, but you could also create a kinetic energy table. Now, I don't think you're probably going to have to solve one completely through, because 2 variables and 2 unknowns is a problem, but this allows me to have 2 unknowns if kinetic energy is conserved. I mean, we know momentum is always conserved. So if you go to solve a problem, it allows you to do that. So you get to say the momentum before equals the momentum after, which I'm going to say in any collision. You also get to say the kinetic energy before equals the kinetic energy after. Now, if you were to have to set up a problem like that, let's say we have a perfectly elastic collision. I'm not going to work this all the way out because I don't think you would have to. But let's say it's perfectly elastic. I'm going to have capital M ball moving at V. And I'm going to have it hit this ball. V is equal to 0, and I'm going to tell you afterwards that this ball M is moving at, let's say, 0.5 V. I want to know what the speed is. So now, if I create a momentum table, I would say momentum before equals momentum after. So I would say mv plus 0 is equal to m times 0.5v plus m times the new v. Now, let's differentiate between these. Let's call this ball 1 and this ball 2, ball 1 and ball 2, m1. This is m1, this is m2. And you can solve from that. The other thing I can also say with this now is I can say 1/2 m1 times v squared plus 0, not moving, no kinetic energy, is equal to 1/2 m1 v over 2 squared, 0.5 v, plus 1/2 m2 times the mystery v, let's call this v final so we can differentiate, times v final squared. And that would allow me to go through and solve the problem now, because now I have two equations. Two equations means you could have two unknowns. And you've done two equations and two unknowns before. Biggest thing to remember is if they hit and stick together, they're inelastic. You're going to lose kinetic energy. It's going to be converted into sound, heat, light, something else. If they bounce off each other, then we're saying that all of it is transferred in. And we know in the real world we don't live that way. So everything we have is somewhere in the middle. We'll deal with this a little bit more in class, and I have a really cool demo I'm going to do with the happy and the sad balls you've seen before. There's one of them so sad. Okay.